All right, time for the fun stuff. Graphing is where we're going to throw this all together. And it's really fun because it's connecting a bunch of concepts and you're kind of putting together jigsaw puzzle pieces. I'm not a big fan of jigsaw puzzles, but I am a fan of math puzzles. So hopefully you're a fan as well. Otherwise, hopefully you can survive. Example 4. Graph the following. And then noting the intercepts. These are all the things you need to include on your graphs. The intercepts, the multiplicities, and the end behavior, which I'm abbreviating as EB. And then this will be our function, f of x equals x minus 1 cubed times x plus 3 squared. And let's graph it over here. All right, so we get to just find a bunch of things and then incorporate them in the graph. So first step is just finding all of these things. All right, so we need to find the intercepts. The x-intercept, that's when y equals 0. Oh, we've been doing this before, right? These are when x equals positive 1 and negative 3. And we know their multiplicities are 3 and 2 respectively. Let's graph in red, make it really stand out. When x is equal to positive 1 and when x is equal to negative 3. Multiplicities tells us something about the shape, but the problem is we know negative 3 is a multiplicity of 2, but we don't know whether it's like this, it bounces, or like this. Not yet, anyway. So I'm going to put a little check mark to show that we've incorporated this part, but we have not incorporated this part yet. Intercepts. Let's also find the y-intercept, right? The y-intercept is when x is equal to 0. Uh-oh. There's not a problem necessarily, but if we plug in 0, you'll see what happens. Becomes negative 1 cubed times 3 squared. That's negative 9. Which is no big issue. That just means that in the x-axis, we'll count by 1. And in the y-axis, we'll have to count by 2. This is negative 10, counting by 2. This is positive 10. So let's draw that y-intercept of negative 9. Great. We've used the y-intercept. We also need the end behavior. What's the end behavior here? Well, we really have to look at the leading term. And again, we don't have to FOIL this all out to find the leading term, although it's a good idea to do so if you want to be extra safe. Just have to look at the x parts. There's an x cubed that's going to come from this part. There's an x squared that's going to come from this part. And there's no numbers that are going to get multiplied by these ones for the x to the 5th part. If this part is uncertain to you, FOIL it out and you get better at seeing it. Get better. I meant FOIL it out and you will naturally improve at seeing it. I'm not just telling you to get good. All right, so the leading term is 1x to the 5th. So we need the end behavior looks like this. So let's incorporate that. It's going up to the right and down to the left. Now we just need to fill in the blanks. So as soon as we know the end behavior, that tells us what these zeros look like. The 0 at negative 3 has multiplicity 2. So we know it's going to bounce off like this. Let's try to connect this. It bounces off because it has multiplicity 2, so it's like a parabola locally. And we know it's down because of the end behavior. Similarly, right, the other 0 has multiplicity 3. So it's going to kind of cross like a cubic function. Kind of like that. Maybe even a little bit more like that. Or maybe it doesn't matter too much. Just get the general idea of that cubic function. All right, maybe like that. And then all that we know is that, all right, well, it has to get really steep so it can curve there. And I don't know where that turning point is. I don't know where that local extremum is. It doesn't have to be like super nice. I'm getting grumpy because I want mine to look nice, but as long as you include the intercepts, the multiplicities, and the end behavior and connect the dots, it's going to be good enough. Let's check our answer and see how well our graph looks, how good our graph looks. So we're looking at this. This is x minus 1 cubed times x plus 3 squared. And when we're checking our graph, let's hit that wrench icon. And in our graph, we're looking from -5 to 5 for x. And for y, we're looking from -10 to +10. So they look kind of similar. What's the difference? So our zeros are right. Whoa. Our end behavior is right. The big difference is that this function actually goes way further down than I thought. All right, so it actually goes like way down there and comes back up. But for a sketch, that's fine. We're not going to worry about finding that local minimum. We're not going to worry about finding where this is until calculus. In the meantime, we're just going to be estimating, and it's okay if your estimate is wrong. What has to be right are this, and that. And connect it. All right, so that's all I'm looking for in something like that. Example 5. 5, we're actually going to do some problems from the book. Number 48 and number 50. All right, we're never going to scroll down that far. Here they are. Use the graphs to write a polynomial function of least degree. All right, so this is going to be number 48 first, and then number 50. We want a polynomial function of least degree. So we're going to work backwards. We're going to identify the zeros, the end behavior, the intercepts, the multiplicities. The zeros are at -2, +1, and +3. Excuse me. What are their multiplicities? Well, each one is kind of crossing like a line, right? All the multiplicities are going to be 1. Let's incorporate that into our answer. I don't know if there's a number in the front. Just put an A there for now. I don't know what scaling that is, but I know there's a 0 at -2, multiplicity 1. I know there's a 0 at +1 with multiplicity 1, and I know there's a 0 at +3 with multiplicity 1. So really all that's left is to find that A value, and we'll incorporate everything that we need to incorporate. And to find that A value, we look at the y-intercept. The y-intercept is +3. So you just plug in that point and solve for A. The 3 is A times when x is 0, this becomes 2 times -1 times -3. Simplify that out. That becomes a +6a. Divide both sides by 6. A is 1/2. So f of x is equal to 1/2 times x plus 2 times x minus 1 times x minus 3. Check your answer. So to check our answer, again, we're going to use Desmos, and we're going to make sure that the scale on Desmos is the same as the scale on this graph. -5 to 5 for x and y. So our guess is 1/2 times x plus 2 times x minus 1 times x minus 3. And we're specifically looking -5 to +5 and -5 to +5. And hopefully this looks similar. Look at the intercepts. The intercepts are the same. Multiplicities are the same. X and y intercepts both. End behavior is the same. Looks like we did good. All right. Let's do one more problem, number 6. Example 6, rather. Find an equation for, just sounded like my cat October just howled, but not like a cat howling, but like a wolf. But she's sleeping. Like the whole, oh, kind of howling. Anyway. Find an equation for a polynomial of least degree four has a root of multiplicity 2 at x equals positive 4, a root of multiplicity 1 at x equals 1, and at x equals 2, sorry, negative 2, and a y-intercept of 0, negative 3. Same thing we did in the last problem. Just now there's no graph. Now we're looking at the information. So our polynomial has a root. Let's underline things as we're using them. Start with the zeros and the multiplicities. X equals 4 is a multiplicity 2. And again, we don't know the scaling factor yet. What else do we have? Multiplicity 1 at these two zeros. So x minus 1 has multiplicity 1, and x plus 2 has multiplicity 1. Least degree 4. This is a 4th degree polynomial. Add up all the multiplicities, you'll get the degree. 2 plus 1 plus 1 is 4. All that's left to use is that the y-intercept is negative 3. So when x is 0, y is negative 3. Negative 4 squared times negative 1 times positive 2. Simplify this or use a calculator. That should be 16, 32, negative 32. Divide both sides by negative 32. You should get a is equal to 3 over 32. Our function looks kind of weird. Should hopefully look like this. Now there's no graph to check our answer against, but we can still graph this ourselves and make sure that it satisfies all the things that we're supposed to satisfy. So y equals 3 over 32 times x minus 4 squared times x minus 1 times x plus 2. Does this have all the things that we need? Polynomial at least degree 4, check. It looks like a 4th degree polynomial. Root of multiplicity 2 at x equals 4. Yep, this has multiplicity 2. It bounces off like a parabola. Roots of multiplicity 1 at positive 1 and negative 2. Positive 1 and negative 2, yep, have the right multiplicities. And y-intercept of negative 3. Y-intercept of negative 3, we did it. We satisfied all the requirements. And that's this video on graphing. Let me know if you have any questions, and I hope you have I like the roots and the multiplicities. I don't know why. I like putting the things together, but let me know if you have questions, and I will help as best as I'm able. Goodbye. And I will check on my howling cat. Saying howling cat sounds like something else, but it's like howling like a wolf. Like, not like that. Yow! Kind of a thing. Anyway.